Hello and welcome to today's webinar, Selecting Proper Heat Exchanger for Process Applications. My name is Tracy Purdom and I am the Senior Digital Editor for Chemical Processing, which is producing this event. This event is sponsored by API Heat Transfer. When it comes to process applications, heat exchangers aren't one size fits all. With a wide selection of heat exchanger types available, how do you know which one is the best for your process requirements? You need to carefully consider many factors, including the type of application, the operating conditions, the properties of the fluids being handled, and any space constraints. In this webinar, you'll learn the criteria used to determine the best heat exchanger for the job, as well as the advantages of selecting one design over another. We'll also introduce you to specialized heat exchangers for especially difficult process applications. To complement this discussion, we will have a live audience-driven Q&A session at the end of the presentation, so please submit your questions as they occur to you. And now I'd like to introduce our speakers, Chris Pollock and Sebastian Schill. Chris has more than 11 years of experience in heat transfer with expertise in both plate and frame and shell and tube technology, and Sebastian specializes in plate heat exchangers for the process industry. Welcome, gentlemen, and I think, Chris, you're going to be the one starting it off for us, correct?
Correct. Thank you, Tracy. This is Chris Pollock speaking. First off, I want to thank everyone for joining us today. We certainly appreciate your enthusiasm for learning more about heat exchanger technologies. So let's start off with telling you a little bit about what you can expect from today's presentation. Over the next 45 minutes or so, we will discuss factors that impact heat exchanger selection, such as temperatures and pressures, and the intended purpose of various applications where heat exchangers are used. We will give an overview of the various heat exchanger features that make them best suited for a particular application, along with some advantages that each design provides. And finally, we will discuss some special purpose heat exchangers and the unique process solutions that they provide. Selecting the right heat exchanger is important and is dependent on several key variables. The type of process is important. Is the heating or cooling taking place as a single phase? Is there phase change occurring? And is there a multi-phase mixture present throughout the heat exchanger? These are important questions to have answered. Fluid types and flow rates are also important. Liquids and gases behave much differently within varied geometries of heat exchanger designs. Physical properties will also affect performance and dictate the style of heat exchanger required. Flow rates and velocities will dictate not only performance of a given exchanger, but determine what type of heat exchanger is needed. Temperatures and pressures are, of course, important factors when deciding on a design. These variables directly impact key design attributes such as material selection and mechanical design details, such as thickness and quality testing requirements. Pressure drop is always a concern when designing a given type of heat exchanger. There are select designs that are better suited for accommodating lower pressure losses at the expense of lower heat transfer efficiency when that trade-off is warranted. Footprint is an important factor as well in the heat exchanger selection. It has become even more prominent in today's world where every inch or centimeter of space needs to be used as efficiently as possible. So we will discuss compact options for heat exchanger design later today as well. For a shell and tube heat exchanger, specifying a TEMA type to the supplier is a significant help when deciding on the type of heat exchanger you expect. A shell and tube exchanger has a large variety of options and design features available, so specifying a certain TEMA type certainly narrows down the field for the design engineer, and we'll discuss more about TEMA types in a few minutes. For a plate exchanger, it is important to check material compatibility, specifically gaskets, with the various process fluids you plan to use, as well as any cleaning or flushing chemicals that may be introduced to the heat exchanger. So the first type of heat exchanger up for discussion today will be the custom TEMA type shell and tube. TEMA stands for Tubular Exchanger Manufacturers Association, and this organization has developed nomenclature so that customers and suppliers can speak the same language when discussing heat exchanger design requirements. Not only was the nomenclature standardized, but various mechanical standards were developed to meet the needs of the marketplace. Mechanical standards are divided into three classes: TEMA Class C for general service, Class B for chemical process service, and Class R for petroleum service. So when you specify a specific TEMA type and class, you can be assured of what you are purchasing. You can find more information on TEMA standards if you'd like by visiting www.tema.org. Now you can see from the figure on your screen that each TEMA heat exchanger style has a 3-letter acronym to designate the front head, shell, and rear head design types. For the front head, types A, B, and N are the most common. Type A is a removable channel with a removable cover so that tubes can be accessed for inspection and cleaning without disconnecting process piping. Type B is a removable channel without the removable cover for a less expensive option with similar features to the Type A. It is also more suitable for higher pressures, typically due to the use of an elliptical head cover, where a rounded cover is better suited for higher pressures as compared to a flat and bolted cover. A Type N is a non-removable channel, but similar to the A with a removable cover. It also has a non-removable bundle. So this can be a less expensive option depending on the pressures, temperatures, and metallurgies required. The integral tube sheet of this design also allows for a small diameter and thinner material with one less flange joint. So in general, the more flange joints you have, the more costly the design will be due to additional weld seams, gaskets, and bolting. On the shell types, E is by far the most common, simple one-pass type shell. And F-type can be employed when a temperature cross exists, which we'll discuss more later, and more than one tube pass is required. The G, H, and X are relatively rare, but can be utilized when shell side pressure drop is a limiting factor, for example. A J-type is typically used when shell entrance and exit velocities vary, as in a vaporization or condensation application, or an expanding or contracting volume of gas. The multiple inlets and outlets split the flow and reduce critical velocities within the exchanger. A K is strictly for shell side vaporization with low pressure drop requirements and can be also useful for a stage of separation and distillation applications. And essentially the vapor-liquid mixture is separated within the K shell and the bottoms are drawn off while the vapor re-enters the column through the top. And on the rear head, the L, M, and N styles have the same features as the A, B, and N front heads we just discussed. And because of that, they're often paired together. The P-type is a floating rear tube sheet suitable for thermal expansion, contraction, and bundle removal. It utilizes packing on the shell side compatible with low-pressure, non-aggressive fluids such as water or glycol, with the more aggressive, higher-pressure fluids such as a hot gas or a high-pressure liquid on the tube side. The S and T are the least cost-effective designs, but they allow for higher pressure on either side with the benefit of a removable bundle as well. The design reduces the ability to have a full tube count, and an even number of passes is typically required as well. The U-tube is also very common. It allows for thermal expansion and a removable bundle. It is also very versatile, but limited to no temperature cross type of applications, which again we will discuss in a little bit. Unless there's an F shell that is used, then the U-tube can be employed with temperature cross. The W rear head is similar to the P, but a bit more cost-effective because of the simpler floating head design, where packing is used on both sides. However, this limits its use to low-pressure, non-aggressive fluids on both sides. It is also limited to one or two passes because of the rear pass rib design. We'll go through a few specific examples of some different TEMA types. Here you'll see an example of a TEMA type BEP. The basic B-type front head is shown in the back of the photo and not clearly shown. The E shell is a simple single-pass shell pipe, and the P-style rear head is detailed in the front with a floating tube sheet and head assembly. In this case, it is also connected to an anti-flanged spool piece for direct bolt-up to process piping. You can see how the tube sheet is sealed against the shell with a packing ring to allow for independent expansion and contraction. Next, we have a typical BEU type exchanger. You can see the B-style front head in the front with the tube side inlet and outlet nozzles attached, pointing up and down. Again, a simple E shell is utilized here, with the U rear head designation shown simply by the bent U-tubes within the shell. Here we have a variation of the BEU, but with a K-type shell, thus making it a BKU. In this design, the front and rear heads are identical to the BEU. However, rather than a simple E shell, we have a K shell configuration. In this case, the K shell is an enlarged shell area to accommodate shell side vaporization with low pressure drop requirements. A boiling liquid will produce vapor that disengages from the liquid in this enlarged shell space and exit the top vapor outlet. Any remaining liquid will exit through the liquid outlet after flowing over the internally mounted weir plate that's shown, which acts as a dam to maintain internal liquid levels. Some of the features of the custom TEMA shell and tube can be generalized as shown. Straight or bent U-tube configurations can be utilized with either fixed or removable bundles as process conditions require. In general, shell and tubes are well suited for higher pressures, 3,000 psi or 200 bar and up, which makes them ideal for severe service applications. There are also heat transfer enhancements available, which we won't have time to get into today, but utilizing these enhancements can increase heat transfer coefficients and boost the performance of the heat exchangers that we have discussed. Please feel free to contact either Sebastian or myself to learn more about the heat transfer enhancement techniques. We'd be happy to review any of those with you after the presentation. So as mentioned earlier, there are many different options and variations of TEMA shell and tube exchangers available. So a conversation with your supplier is highly recommended to ensure you're receiving the best solution for your specific process. Discussing your needs and the options for meeting them prior to preparing thermal designs is the best approach, and any good supplier will welcome the opportunity to have that conversation with you. So what are some of the advantages of a custom shell and tube exchanger? Well, the round shape of the shell and tube vessel makes it an ideal choice for high pressure applications. There are minimal gaskets required on most designs, and there are many varieties of gaskets available on the market that can meet the most stringent requirements where the gaskets are needed. Flexibility and design features such as shell sizes, tube counts, and pitch make the shell and tube well suited for large volumetric flows, especially when there's a wide differential of flows between the shell side and tube side. The tube side of a shell and tube is also easily cleaned by chemical flushing or mechanical brushing of the tubes. The head channels or covers simply need to be unbolted, providing access to the tube sheet and the tube internals. This is a simple maintenance procedure in most any service. Again, some typical applications. The TEMA type shell and tube is very versatile due to the many design variations available, so there are many typical applications. Hence, most applications can be suitable for some type of custom shell and tube, including general heating and cooling of single-phase fluids, along with vaporizing or condensing applications, which can all be well handled by these exchangers. I will turn the presentation over to Sebastian now for a review of some gasketed plate heat exchangers.
Okay, thank you. So, first of all, I want to speak about gasketed plate heat exchangers. Some words about the working principle for those for you who are not familiar with the plate heat exchangers. So there's a hot and a cold fluid exchanging the heat from the hot fluid to the cold fluid. The fluids are therefore handled in channels, as shown on the picture. There's typically the hot fluid going from the top to the bottom, and the cold fluid going from bottom to top. The reason that the cold fluid goes from bottom to top is simply that in case of evaporation, the gas phase would go upward with the flow of the fluid. Every second channel contains the same fluid. The picture shows a so-called single pass unit with all connections at the front fixed head. There are also multi-pass units possible in order to extend the time the fluid is heated or cooled. In this case, you will find connections also on the movable cover of the plate heat exchanger. The plates between the fluids are corrugated to increase turbulences of the fluids and therefore increase the heat transfer. Turbulences give pressure drop as well as heat transfer. So just a small example, cooling a hot tea in your cup. If you use a turning spoon, it is more efficient than if the cup is just standing still. This is because the turbulences increase the heat transfer. Furthermore, the corrugation is important to stabilize the plates against the working pressure. The plates contact each other at the contact points and when they are mounted in the heat exchanger. Let's have a deeper look on the countercurrent flow as shown on the picture. Countercurrent flow is identified as the most effective way of transferring heat from one side to the other side. Heat exchangers that can use this flow direction are more efficient than others. A plate heat exchanger has the best configuration to arrange the flow in a countercurrent way, while a shell and tube heat exchanger is typically a combination of cross-flow, co-current flow, and countercurrent flow. The baffles and the tube arrangement guide the flow typically in the way as shown on the right side. This is why a shell and tube heat exchanger needs a correction factor that is obviously below 1 on the LMTD to compensate for this flow pattern. Let's have a look on the gasketed plate heat exchanger in more detail. The minimum material for thermal plates inside the heat exchanger are low-grade stainless steel like 304, 316L. Higher grades of stainless steel can be pressed as well, like 904 or SMO, nickel, nickel alloys, titanium, titanium alloys. The material selection is, however, limited by materials that are able to withstand the big deformation that is done during pressing of the plates. Gaskets are typically made of rubber, such like nitrile or EPDM. Also, some fiber gaskets are available. The gasket is the biggest limitation in gasketed plate heat exchangers, both in terms of pressure and temperature. Due to the high thermal efficiency, the plate heat exchanger is typically much smaller and lighter than a shell and tube heat exchanger. Furthermore, more surface area can be installed on a smaller footprint. Additionally, there is less space between the plates than between pipes. This is why the hold-up volume is also smaller. This is especially interesting if you have expensive or dangerous fluids. Due to the strong countercurrent flow, it is also easily possible to have crossing temperature applications. It is possible to go down to only 1 Kelvin between the fluids. So you may have water from 6 to 12 degrees Celsius on one side, and on the other side you just have cool down the hot water from 13 to 7 degrees Celsius. So very close approach. As the plates are held in place by so-called carrying bars and tie rods, it is easy to assemble and disassemble the heat exchanger on site. Furthermore, you can add or remove plates in your application. By transforming the flow arrangement internally, you can set new configurations in an existing plate heat exchanger. Nothing is welded here that would require welding work to put a new configuration in place. Where do you use gasketed plate heat exchanger? As we have seen, the strength of plate heat exchanger is the high efficiency. Therefore, they are typically used when there is a close temperature approach or even a crossing in temperatures. Economizers demand typically these kind of temperature profiles as the aim is to gain as much heat as possible by cooling a fluid after some treatment. Also, if you want to heat or cool the liquid over a bigger temperature range, for example from 10 to 100 degrees Celsius, a plate heat exchanger shows his compact advantages as you can build multiple passes in one heat exchanger easily. The high efficiency is optimized when the volume flow on both sides are not far from each other and the flow is all in liquid stages. Gases can be handled in gasketed plate heat exchanger as well, but to a low extent. So let's move to all-welded plate heat exchangers. In our company, they are called Sigma WIG. They are used in a wide range of applications, especially in the chemical industry and also in the refineries. Again, we have the pure countercurrent flow, like in the gasketed plate heat exchanger. The plate pack is installed in the same way into a bolted frame. Difference is that the gaskets are replaced by welds. This includes also the gasket to the connection flange. So the complete heat exchanger is welded and does not contain any gasket at all. In our Sigma WIG, there is no contact between the fluid and the frame material. The plates are typically made in stainless steel, nickel alloys, or titanium, and are pressed with the similar corrugation than gasketed plates in gasketed plate heat exchangers. The advantages of the Sigma WIG type all-welded plate heat exchanger show the similarity to the gasketed plate heat exchangers. The small footprint, the high efficiency, as well as the hold-up volume. As the all-welded plate heat exchanger cannot be opened like a gasketed plate heat exchanger, it is a big advantage that the high turbulences in the channels make sure that there is a good self-cleaning effect. The fouling factor that is typically used in plate heat exchangers is only 10% of the one used in shell and tube heat exchangers. When the gasketed plate heat exchanger cannot be used due to pressure, temperature, or the aggressiveness of the fluids for the gasket, then an all-welded plate heat exchanger comes in the picture. Therefore, the typical applications are similar to gasketed plate heat exchangers, but with a focus on chemicals and pharmaceutical industry. As you can see also in the lower picture, the channels between the plates are quite small. This gives us the high efficiency, but limit also the range of applications to only clean fluids. Let's move on to the all-welded plate heat exchanger. What you can see here is a so-called plate and shell type heat exchanger. It is a combination of a shell and tube heat exchanger and a plate heat exchanger. From the outside, it looks similar to a shell and tube heat exchanger with a shell side and a tube side. Internally, the tubes are not there. They are replaced by a plate pack, which you can see on the right side. The laser welded round plate pack is installed into a round shell. Here you can see on the right side the flow inside such a plate and shell heat exchanger. These plate and shell heat exchangers can be provided in fully welded design or in an openable design to extend or extract the plate pack. The design is very flexible in terms of connection sizes on the shell side, as there is no limitation given by the plate holes. This gives the possibility to use these units also as condensers, evaporators, or even for complete gas applications on the shell side. Compared to other plate heat exchanger designs, the round shell allows also higher operating temperatures and higher operating pressures. They are far beyond what you normally see in gasketed plate heat exchangers, or also in other welded plate heat exchangers. Very compact design, and therefore it's typically with lower weight and with larger surface area in a smaller hold-up volume. The self-cleaning effect due to high turbulences between the plates allow it to use it as also for dirty applications. Plate and shell type heat exchangers are typically used for applications with close temperature approach and higher pressures and higher temperatures, but also in applications where the fluid is either dangerous or of high value due to the low hold-up volume. So, Chris, may go on.
Thank you, Sebastian. Now we'll discuss a specialized variation of a shell and tube exchanger called a hairpin exchanger. Over the next few slides, you'll see that the hairpin offers some unique advantages that are well suited for a variety of applications. A hairpin heat exchanger gets its name from its shape. As you see in the photo, it looks like a hairpin, as someone would put in their hair. And it is in essence the same as a straight tube heat exchanger bent fully in half. The front and rear heads are similar to TEMA type A, B, or N styles, and each shell leg follows the E-shell style design. There are a few features that make a hairpin an ideal choice in process applications. They can be offered as a fixed bundle. This is an all-welded design, typically similar to an NEN or a BEM style, again, bent in half. They can be offered with removable bundles in two subsets of designs. A common closure has one set of flanges and bolting, and a separated closure which has two sets of flanges and bolting. The common closure is a lower cost option, but good for lower pressures and temperatures. The separated closure is good for higher temperatures and pressures, but comes at a slightly higher cost due to the additional flanges and bolting required. Materials available are typical of a custom type shell and tube and can cover a wide range of fluid compatibilities. Shell diameters are typically in the standard pipe size range, but larger shells can be provided with customized closures. When larger shell diameters are needed, the processes typically don't require long lengths, so in these cases, a typical custom TEMA type might be suitable. Design pressures typical of a TEMA shell and tube are common, again lending flexibility as an alternate to the more traditional shell and tube heat exchanger. And lastly, standard support and channel designs are stackable, making multiple hairpin units piped up in series or parallel a very easy design option. Key factors that make a particular application well suited for a hairpin: compact footprint. The bent in half design lowers the required installation footprint for the exchanger, along with less bundle removal space required for maintenance. A hairpin will be lower in weight when compared to the alternative of multiple TEMA types in series because there are fewer flanges, no interconnecting piping, and fewer channel materials. There's also more efficient use of the surface area by utilizing a continuous shell side chamber, leading to smaller overall size. And lastly, the use of a U-tube design allows independent expansion and contraction of the tubes and shell, eliminating the need for an expansion joint. The typical process applications that can take advantage of these design features are those that have a temperature cross, as one example. Process conditions that include a temperature cross typically require very long TEMA types or multiple units in series. Again, for reference, we define a temperature cross as when the hot side outlet temperature is lower than the cold side outlet temperature, and thus the temperature profiles of each fluid cross each other. Typically, an economizer is tasked with providing the most heat transfer possible for a given amount of surface area. For these high-duty, heat-duty applications, a hairpin is a great solution. A consequence of maximizing heat transfer between two fluids is that the tight temperature approach is created. A hairpin design provides a better solution than a very long TEMA type, or again, multiple TEMA types in series, by limiting the footprint required for tight installation spaces. The U-bend design allows independent movement for thermal expansion in high temperature differential environments, which again lends itself well to a hairpin design. Where a traditional U-tube may not be a good solution for this due to a temperature cross or a temperature differential across the tube sheet, the hairpin offers true countercurrent design and thermally separated tube sheets. As previously discussed, the hairpin is also a better option when multiple long TEMA types would be required in series. Next up is one of the more niche shell and tube designs, which is a double-tube sheet exchanger. When leak protection is a critical concern, the features of the double tube and double tube sheet design are a great solution. The double tube sheet design looks very normal from the exterior. One would assume it's a simple TEMA NEN or BEM type exchanger, but inside is where all the engineering comes to the forefront. A unique arrangement of multiple tubes and tube sheets creates a layer of leak protection that can allow the end user to rest easy on applications where a cross leak of fluids simply cannot be tolerated. As mentioned, the TEMA type NEN or BEM are the typical design basis, but process fluids are separated by a neutral intermediate fluid that serves as a barrier between potential cross leaks. The design basis consists of inserting a smaller OD tube inside a larger OD tube. There is a small annular space between the tubes that serves as a chamber for the intermediate fluid to be introduced. There's also an inner and outer tube sheet at each end, between which a chamber is also formed, continuous with the annular space between the tubes. This entire internal chamber isolates the tube side from the shell side and will capture any cross leaks that occur in operation. For example, a ruptured tube or tube sheet joint will first fail into the intermediate fluid, which can be detected through pressure monitoring. And of course, as with common TEMA type exchangers, multiple material options are available for proper compatibility with process fluids. Again, the advantages of this design are that it virtually eliminates the potential for cross-leak contamination. The use of an intermediate fluid, like a glycol, for example, minimizes thermal conductivity losses as compared to a design that might utilize simply an air gap in between. And finally, through pressure monitoring of the intermediate fluid, a failure can be identified and rectified immediately. Some typical applications that might require the added leak protection are those that include potable water, for example, where maybe a water source is repurposed as a heating or cooling medium, or a high-pressure flammable gas against a glycol for a cooling or preheating application. This is a case where any gas that leaks into the glycol could pose a fire or explosion hazard in a process plant. Also, in many cases, a natural resource, such as a lake or a river, can be used as a lubricant coolant or a process fluid coolant. In these cases, the process fluids can obviously not re-enter the surrounding environment, and the double tube sheet design will provide extra safeguard against that. For another specialized heat exchanger, I'll turn it back over to Sebastian.
Yep, thank you. So we want to talk about graphite heat exchangers. It's a special product. It's our last product that we want to present to you. The graphite heat exchanger is made by blocks or tubes that can allow strong acid or other corrosive media to be heat treated. On the right side, you can see a typical block graphite heat exchanger. And you can see next to it a small graphite block that is installed in such a heat exchanger. Graphite is a quite fragile material that on the other side comes with a very good thermal conductivity, much higher than stainless steel, for example. Within the last years, the graphite heat exchanger was improved on performance as well as on stability. But the most important feature is the outstanding corrosion resistance. Graphite block heat exchangers come with a compact design made in a modular way. This allows cleaning of the individual blocks. A special buffer system allows to optimize the flow through the blocks. On the right picture, you can see a multi-pass arrangement of such a block heat exchanger with many passes to gain heat in an economizer. So the buffer system is the thing on top that is at this moment mounted on the graphite blocks. And then the carbon steel or stainless steel shell will come around this buffer system. Graphite heat exchangers are typically cheaper than their alternatives made in special alloys like tantalum or zirconium, because these are the typical metals that can also withstand the acids that are treated with graphite heat exchangers. Graphite heat exchangers are only used for applications where standard metals cannot be used. They can replace heat exchangers made in these special materials. Examples are treatment of hydrofluoric acid, nitric acid, or higher concentrations of sulfuric acid. So, I hand back over to Chris.
As we conclude today's webinar, I'd like to just give a brief summary of our company and then open things up for some questions. API Heat Transfer is a global company with our headquarters in Buffalo, New York. But we have multiple facilities across the globe, staffed with a team of engineers ready and willing to help wherever you need them. Through this network of engineers, we can consult with you engineer to engineer and discuss the best technical solutions for your specific application. API is not a new company. We have technologies that have been in the market for over 130 years. So we have seen the best and the worst that process applications can offer. And finally, we have a broad array of products to meet the needs of the market. Only a few of those were discussed here today. But process plants have many different applications and heat transfer needs, and API can be your one-stop shop for all those solutions. I'll put up our contact information here again. Please feel free to contact either Sebastian or myself via the phone numbers and emails shown here. We are more than happy to discuss today's presentation in more detail or help you with a specific heat exchanger application that you might have. That concludes our presentation for today. We hope you found it educational and interesting. So thank you once again for attending, and at this time, I guess we'll turn it back over to Tracy and answer some of your questions.
Yes, exactly, Chris and Sebastian. We've got a lot of good questions coming in here from our audience members, so we're going to get to those right away so we can fit as many as we can in. The first one is an easy one. Where are your heat exchangers built?
Well, that's an easy one. Of course, here in Buffalo, New York is our headquarters, but we also have multiple facilities across the globe. It really depends on what type of heat exchanger you're looking for and where it's going to go, but we have facilities in Europe, in China, Asia Pacific, and in the United States.
All right, thank you. Another question here is there any national or international code or standard for plate heat exchanger?
Yeah, generally a plate heat exchanger is looked as a pressure vessel. So the typical pressure vessel code applies for plate heat exchangers. Even though there are, for example, in China, some exceptions because there it is not 100% regarded as a complete pressure vessel. But in the Western countries, Europe, and it's completely looked as a pressure vessel. So the code is ASME, PED in Europe, CRN, and all the local codes.
All right, thanks, Sebastian. Another one on that kind of same vein is can you comply with specifications like API 660 or ISO specs, for example?
Yes, of course. Those are very common specifications. There's variations of them for shell and tube and plate and frame, hairpin, various different types of heat exchangers. We've seen them all. We even go one step further and try to work with the customers and end users to identify parts of those specifications that they may not need, that may add cost. So we try to point those out and work with our customers to keep the cost down.
All right, thank you.
Yeah,
weighing back. I'm sorry. Go ahead, Sebastian. I'm
yeah,
sorry.
just in addition to the plate heat exchanger discussion we just had, so there's also an API standard for plate heat exchangers, which is API 662. That can be applied to plate heat exchanger, and it's quite common to use this standard.
All right, thank you. What type of materials can you provide?
It's different for shell and tube and plate and frame somewhat, so I'll let Sebastian comment on the plate and frame materials.
Yep, so the thermal plates can come typically in stainless steel, different kinds of grades of stainless steel. Titanium is the second, which is often used, and then nickel alloys, Hastelloy. The requirement that it has is that it can be pressed, so it does not crack when it is deformated in our press lines. So materials like duplex steels cannot be pressed and therefore cannot be used for plate heat exchangers.
And on the shell and tube side, it's basically limited to commercial availability. So, I mean, the common materials are carbon steel, stainless steels, higher stainless type alloys. But we can work with things like titanium and Hastelloy as well. So it really is based on what's out there in the marketplace that we can purchase as raw materials.
All right, thank you. Another question here is, do you have hygienic design criteria for both the plate and shell and tube exchangers?
For the shell and tube, we don't get into the sanitary hygienic market. This is more process oriented. On the plate and frame side, it's more of a larger market for us. So we can meet some of those standards on the plate and frame side, but not as much on shell and tube.
On plate and frame, the most common use is 3A standards. Then there is a special design which is called the double plate heat exchanger, or Sigma Twin in our case. It's similar to the shell and tube heat exchanger that was just described. With double-tubesheet, so it's the same thing done in plate heat exchanger. And then all the gaskets that are used in this field have GDP performance or stamps.
All right, thank you. A lot of questions like these coming in. Is there an equivalent to TEMA for plate and frame?
No, not to that regard. Yeah? There is the API 662 that defines the general rules. And on the other side, let's say the variety of plate and frame heat exchangers is much smaller than on the shell and tube side. So, for example, the TEMA type describes the head and the rear for shell and tube, for plate heat exchangers, this is always the same. So there is no variety in this regard.
All right, thank you. They're coming in fast and furious, so I apologize for throwing these at you real quick like this, but can you also provide graphite heat exchangers in a shell and tube configuration?
Yes, so we can do also the tubes in graphite, so that one side is flowing through the tubes. The tube side can have acid, and the shell side would be cooling water or steam, whatever it is. Yes, so the design is available in block type, in shell and tube type, and in addition it's also available in plate type. So you can get a complete plate heat exchanger also with graphite plates instead of stainless steel or metal plates, in general speaking.
All right. Would it be recommended to use a plate and shell heat exchanger as an evaporator or a condenser?
Yeah, it's not even recommended. It is highly recommended because this is a big strength of shell and plate heat exchanger. So because you are flexible with the connections, on the shell side you can put a very big nozzle on top and you can have a small nozzle on the bottom of the shell, so you can evaporate in the plate pack or condense in the plate pack if you do it the other way around, and you have your cooling media or your heating media on the plate side.
All right, thank you. Another question here. Any application where you cannot use plate and frame?
Yeah, for sure. For sure, there are a lot of applications where you cannot use them, especially if you go to very dirty process, because then you do not have a plate heat exchanger, then you have a filter. But you just filter with the plates, right? So this is not what you want to do. You want to exchange the heat. So dirty applications, you cannot work whenever you have a big amount of fibers or longer fibers, let's say fiber that are longer than 3 millimeters, they're already a problem for plate heat exchangers. And the other limitation is certainly the pressure and the temperature, because I mean the option you have is a shell and plate heat exchanger, but also there is a limitation in temperature and pressure. And then the material selection, because plate heat exchangers can only be done in the materials that can be pressed to plates. So as mentioned, the duplex materials cannot be used, for example.
Now, this is just a question on top of that. What happens when people do try and use that? What are the consequences?
Excuse me, can you repeat?
What are the consequences if they ignore that advice and do use that?
Oh, that depends on which advice they will ignore, right? So if I mean, pressure and temperature is quite obvious. It will fail, right? And will damage, it's not dangerous, but you will damage the internal plates, because the plates in plate heat exchangers are made from steel that is only 0.3 millimeter, 0.6 millimeter, 0.7 millimeter thick. So if you operate them under too high a pressure or too high a temperature, you will deform them, yeah? Or you will damage the gaskets, especially on higher temperature side, you damage the gaskets inside. In terms of fouling, I mean, or dirty fluids, you will plug the heat exchanger. So you increase your pressure drop until it's completely plugged. Then you have to open it and clean it, which is possible. Yeah, if you do not look at the advice of what I mentioned with like 4 millimeter fibers, for example.
All right, thank you. Another question here. What are some major problems encountered with use of shell and tube heat exchangers?
The typical problems you'll see in the field are fouling and corrosion. So it's very important to discuss the fluids and the application with the design engineer so that proper fouling factors can be used, proper materials can be used to increase the lifespan of the equipment. By far the most, when we see replacement or bundle replacement requirements, it's usually because some portion of the heat exchanger has corroded over time or it's been fouled beyond cleanability.
All right, thanks, Chris. Another question here. When is it advisable to use baffles, and what are the determining factors for the best design of baffles?
Well, baffles are always advisable to use. If you don't use the baffles, you're not getting a good mix of shell side fluid. There are cases, certainly, where specific types of baffles are used or not used, where that type of turbulence isn't required. But for the most part, you're always going to have some sort of baffle. The spacing and the baffle cut is important. It dictates the heat transfer coefficient on the shell side as well as the pressure loss through the shell side. So there are various different geometries of baffles that can be used. It's hard to answer that specifically because they are very process specific. But generally, there's things like single segmental and double segmental baffles. And again, the cut of those baffles is a common variable to adjust in the design as well.
Thank you. Going back to that analogy of the hot tea with the spoon in there, so it makes sense.
Yes.
All right, next question here is, what is the sensitivity of plate heat exchanger to delta P and velocity?
Yeah, to that question, it is recommended, or it is optimum, let's say, when you have the same flow on both sides, so the same volumetric flow on both sides of a plate heat exchanger, then you will get out as most as possible, because the channels inside of the plate heat exchanger are always the same on the cold side and on the hot side. On a shell and tube heat exchanger, you are much more flexible in this regard. Like for this kettle type heat exchanger, what we saw before, you have a big space on the shell side and a small space on the tube side. This variation is not possible, let's say, to do in a plate heat exchanger. So, but as long as you have similar flow rates on both sides, then it's the optimized solution with a plate heat exchanger.
All right, another one of our audience members wants to know, can we clean a plate heat exchanger by induced countercurrent flow or reversing flow's direction without significant damage of gaskets?
Yeah, that's a very good question, because, yeah, of course you want to clean a plate heat exchanger without having always to open it. Yeah? So it is recommended to do cleaning without opening, if possible. And these are actually good ways in the question. So yes, it is possible for sure to back flush, or yeah, to just go in the other direction. If possible, you increase the speed, so you increase the velocity during this back flushing, so you have higher speed while cleaning. And to the question whether you harm gaskets, you will not harm any gasket by flowing water or cleaning fluid or whatever you want to use for the heat exchanger in the backside. So the gasket design is the same in both sides. The gasket is not affected, or is not interested, let's say, in where the flow comes from.
All right, thank you. We have time for a few more questions here. One of them is, can you comment on the problems associated with using excessive fouling factors in the design of shell and tube heat exchangers?
Sure. The easy answer there is you're going to over-design the heat exchanger in terms of excess surface, so you're going to make it larger and more expensive than it needs to be if you're too conservative with your fouling factor. The other thing is, in the initial clean stage, it's going to significantly overperform what the heat exchanger was rated for in the fouling condition. So your temperatures will be either hotter or colder than you initially planned because the heat exchanger is clean in the beginning. So you have to have a means of compensating for that in your process.
All right, and last question here we're going to squeak in. How is pitch geometry decided, 90 versus 60 degree?
Sure. That's relative to the tube pitch. And there's the main reason there is is obviously the fluid dynamics and the shell side of the heat exchanger. 30-degree pitch is a very common one, but we could call it the standard. And then you vary from there based on things like pressure loss through the exchanger. While you can vary baffle spacing and cut to help with pressure loss, the tube pitch can also be used for that, as well as bundle entrance velocities. So based on how the tubes are oriented, the fluid dynamics will impinge on the tubes with a higher velocity with certain pitches as opposed to others. So you can adjust that to eliminate that problem.
All right, Chris and Sebastian, you did a wonderful job of answering all these questions last minute here. The presentation, which is packed full of so much information, we appreciate your time and expertise on that. Audience members, did you like this presentation? Let us know your thoughts by answering a brief survey. That'll be posted up to the screen in a few minutes. Your candid answers are not only appreciated, but they always help us craft future events. Remember, this webcast will be available on chemicalprocessing.com. You'll have access to the on-demand slides, so you can get a capture of those slides that were maybe too much, very dense with information. You can take a better look at those. Also, at the end of this presentation, you're going to have access to that handout that I told you about, the exclusive heat exchanger guide. Feel free to log in and view this webinar again, or encourage your colleagues to view it. We also hope that you'll visit chemicalprocessing.com to gain access to even more tools and resources aimed at helping you achieve success. On behalf of Chris and Sebastian and the folks over at API Heat Transfer, thank you for your attendance, and we hope you have a great day today.